first workshop of the day, and I'd like to thank everyone for coming, because thanks to you, I won a bet with my father. He seemed to think that only 20 people would be crazy enough to want to build their own solar panels. So thank you. Look around. This is a room full of crazy. Thank you. Okay, this is what we'll cover, or actually we'll try to cover during the course of this, because we have a lot of information. We're going to do a very quick overview of solar cells. We're going to discuss everything that we purchased to build the solar panels and the design decisions that drove them. We're going to talk a little bit about costs. We're going to go step by step. We also put aside some videos so that you can watch some of the process of the tabbing and the encapsulation. And then if we have time, we're going to get to the storage, implementation, and the future of where we see this going. Okay, this actually isn't our quote. If you haven't worked with high current DC before, do some reading or talk with someone who has done. This all started as a series of blogs on Earthineer. And this was actually a comment from somebody, and we got a chuckle over this. This is my why you should actually listen to us page, because we have a lot of electrical experience. My father actually, he owns his own company. He builds high power transmission systems. So he's on a regular basis he's working with 30,000 volts. So it was kind of comical that somebody should say that be careful with working with the solar panels. Okay, so why build your own? It's very easy, the cost. We actually wouldn't have gotten into this and built our own solar panels this year if we hadn't found a source of really cheap solar cells. The standard price happened to be somewhere around $2, thanks to a lot of economic uncertainty. China was offloading a bunch of solar panels. It drove a lot of US manufacturers under. And because of that, a lot of them were going to auction on some of the materials. We got our solar cells at 27 cents a watt, and that was actually after somebody had gone to auction, purchased it on pennies on the dollar, and then we paid him for, so obviously he marked it up from there. But these were the costs to do it on ourselves, and this is based on a 6 kilowatt system, because that's how many solar cells we actually bought. So it's going to wind up being 30 panels altogether. So the total cost by the time that we're done with this is $5,370. And the cost to purchase the same type of system, new and installed, would have been $45,300 before you start getting all sorts of credits for it. So that probably would have driven it down to $30,000. But you always hear about purchasing solar cells as being a long-term investment. Unfortunately, I would never purchase solar cells if I didn't have the money. I'm not going to get in debt just to purchase my solar cells so I can get off the grid. So this was always something in the future for me until we actually found things cheap enough to do it. So here we have the boxes are 6 kilowatts worth of solar cells. And when it says fragile on the box, they really are very, very fragile. Okay, the basics of solar cells. This is probably very, very simplistic for all of you, but the term is photovoltaic. Sunlight comes in, hits a semiconductor surface, you get voltage out, and then you can do something useful with it. So here we have the front of the solar cell and the back. So you can think of them like batteries. They have a negative and a positive connection. So you just flip them over. So the specs, 3x6, 0.5 volts at 1.8 watts each. Okay, so if we go back to the battery concept, you can think of solar cells in the same way where you can go ahead and put them in a series or parallel. So if you do it in a series, the voltage adds, but the current stays the same. And if you do a parallel, the current adds, but the voltage stays the same. So we have the basic formula, the power in watts is equal to current times voltage. So now that we have all that, we can then do something useful with it. So what we did, and we're doing 36 cells in series, 3 strings parallel. What this is going to wind up being is we're going to have the total voltage is going to be is 18 volts. And that's before we'll obviously have the controller controlling it to 12 volts. So that will wind up totaling 108 cells. So what we're expecting out of each panel is about 194 watts in optimum conditions. So in building the panels, we're going to be covering 3 different things. The framing, the covering of it, and then the encapsulation. Okay, we'll start with the framing first. We went ahead with aluminum channels. You could go some of the do-it-yourselfers go the wood route. We wanted something that would last quite a bit longer. And thankfully, we had a lot of equipment back at the shop where we could cut pretty precise angles with this. So we wound up getting the 1/8" aluminum L, 1 inch by a 1/2 inch. We actually happen to have a lot of this in excess back at the shop, so we were very fortunate in that respect. But there are a variety of sources that you can get this. McMaster Car, that's one that we go through a lot. Local metal suppliers, eBay, wherever you can get it the cheapest. All you're looking for are channels to do the work. Okay, so we'll go over covering next. Commercial, typically what they're looking at is tempered glass, low iron. We had seen some of the do-it-yourself for plastic, and that was actually the very first thing that we looked into. But what we discovered, the plastic was actually pretty expensive, and the scratch resistance was even more expensive. So what we wound up doing was we had found a source for tempered glass. Some of this process, unfortunately, we can't always give you the manufacturer to go to, because in this case we had just found a guy who lived 7 hours from us. We drove there, picked them up. He had ordered in bulk, probably from an auction again, tempered glass specifically for solar panels. So we found him 7 hours away. We drove there. We got it at $25 a sheet. Okay. So when we put them together, we're going to be putting the aluminum channels together with the tempered glass. We constructed it with expansion in mind. We have an 1/8 of an inch clearance around all of the cells, and you'll see that later. We have 3/16 clearance of the glass to the frame, and then we had holes that were drilled and tapped with 832 stainless steel screws. And then we went ahead and took a silicone caulk around the entire frame, and then laid in the tempered glass into that. And then once that was in place, we went ahead and hit it with another bead of silicone caulk on top of it. We also went ahead and added in aluminum braces, and I think these were actually weren't they? Yes. Okay. So I was wrong with it actually being L crossbreed. But anyway, we just added that for extra rigidity. That was the only reason. And on either side, we had screws there so that we could take those out. So we're going to be laying in all of the cells, doing the encapsulation, then putting that back on. And the only purpose was just to make it a little bit more rigid. And actually, I'm kind of surprised this is in here. Hold on. Okay, so when I put this presentation together, we created a lot of videos for it because I thought that would be a good way to give you an introduction to what was done. So we're going to go over some of the tabbing first, and I won't talk for a while.
Well, what you got to do is you got to prepare the surfaces with a flux. Use the rosin flux. This stuff is really good for doing this, mostly because the tip is almost made for this. What I usually wind up doing is going ahead and applying some to the tabbing material. In many cases, you really don't need to do that, but I found that it does indeed help. And then what you have to do is you have to take the flux pen then and put a very fast and thin layer on this center area where you're going to put the tabs down. And what you want to do then, and what was good about putting the flux on this thing is that this stuff is now tacky. so it'll help hold it in position. What I usually wind up doing is let the solder itself be the thing that holds it, and then position this so that when it does indeed lie down, it should lie down flat. Now some of this is, you really do have to have a good soldering iron, and preferably one that's temperature controlled. I found that setting it around 400 degrees C works really, really well. And I usually prepare the iron a little bit by putting just a couple drops of solder on there so that the solder will flow. Then once I have it kind of held down in position here, then you go ahead and allow it to start. And you can kind of see the reflow on there. You can kind of see where it's actually melting the solder on the soldering tab. And the soldering tab is prepared already with some solder on it. But I wind up using a little bit of extra solder here just to make a good, solid electrical connection and thermal connection. And that's it.
And I hope you don't mind that we go through some of these videos we prepared. It's probably a good 13 minutes of this, but this was the best way to do this. Hold on.
Flux.
We thought this was the best way to do it so you could actually see the entire process.
First thing you got to remember is that these things are almost like dealing with eggshells. They're very, very fragile. Now, when we first did our initial one, we used these same things that are here now, but we did everything one at a time. So these are nothing more than the tile spacers. And use these to help hold everything in position. But then finally realized it was a lot better to handle these things as a group rather than as individuals. And you can go a lot quicker if you set up a jig with these things actually glued down in place, and then you can just follow from one to the next one. Now, one thing you never want to hear is a little bit of snapping, because that means you've broken one.
Yeah, we have some broken ones over there if you really want to see. They are like eggshells.
I'll let you know sooner or later you will break one.
Oh, just the flux pen.
Once these things are positioned up and you're happy with the placement and stuff, then you can go ahead and start tacking these things down. Now, the best way I've found to do this is to just go ahead and put it in the center of the thing and then drag it off. It doesn't wind up, you don't wind up with exactly the prettiest solder job, but you wind up with a good electrical connection, which is all I've been worrying about. For some reason, the backs of these things are a lot harder to solder than the fronts are. And I don't know if it's a different material or what the story is, but it's just more problematic about getting a good joint. But I like to see flow off to either side of this thing so that you've given it as much of a possible of a good joint as you can.
Now, you're going to be spending a lot of your time on the tabbing. I'll tell you that ahead of time. How much did you estimate that it was actually the length of how much tabbing and the wire we would?
We're going to be about 3 miles of tabbing by the time we're done.
Oh, and don't worry if you don't happen to catch or remember all of this, because we do have a YouTube channel too, so we just went ahead and created a playlist so you can view it again, and we're going to wind up putting something up for a complete step-by-step anyway. So don't feel you need to take copious notes.
What we're going to wind up doing is to take these things out, but you have to be very slow, very gentle, because these things may want to still stay down.
And break.
Believe it or not, they didn't break. Those little snaps that you heard, it was just coming out of the jig. So I've usually been trying to put something under it so I can carry it all at once. That'll be it. Commercially, they use a whole bunch of suction cups to go ahead and to handle these things as a group. So each one of these cells should produce about 1/2 volt. So what we're looking to do is to go ahead and to test at various stages and stuff while we're putting things together, make sure we don't have a problem. What we wind up doing then is putting a bank of fluorescent lights down and then coming and measuring across the groups of cells just to make sure we don't have a wiring error or anything else. So what we should see then is somewhere close to 4 volts. 3.77 on this one. Next one down. 3.77.
Yeah, the last thing you want to do is find out you have a wiring problem after you encapsulate the whole thing.
So 3.86. 3.86. We also tend to get very nervous about this point. 3.99, kind of as I expected, is it go in toward the center because there's a little bit more light in here. It's going up. And you also have to realize the configuration that we made on this is not the only way to do it. It's just you make decisions on the amount of voltage that you need and the amount of current and power that you want to get. 177. 72, 3.72. So all of these strings down this way are all I would consider good.
Okay, we're going to step into the actual encapsulation process next. I should have some additional slides here, so hold on. Okay, we already covered tabbing, encapsulation. Okay, so here were some of the decisions that we had to make. Commercially, what we found is that they use EVA film, and they laminate everything together. There's only one downside to that. It requires an open vacuum chamber. We had seen some do-it-yourselfers attempt the same sort of thing with a heat gun, but we were a little concerned about some of that. So our option was that we decided to go ahead and do a poured acrylic-like resin. And we had stepped through several of them. The first we went with what was something from Dow Corning, which actually wound up being pulled from the market right after we finished our very first panel. It seemed to work well, so I'm not sure what the concern was. Was it something, were you sure, why was it pulled?
It was an environmental protection issue, I believe.
Okay.
That Dow got into some sort of a trouble with the EPA. Imagine that.
Yeah. Well, the next one we tried we felt was a little too viscous because what we were looking for was we wanted something to flow and we didn't, because we needed to get underneath all the solar cells. And we needed to not have a lot of air bubbles. So when we found, when that was too viscous, we decided not to go with that because we were concerned about having air bubbles underneath. So that's the very last one on the list. That's what we wound up going with, and that's what you're going to see on the poured encapsulation here. There are two parts to the encapsulant. There's a part B and a part A. So what you have to do is you have to mix these two before you wind up using them. So you wind up just pouring the stuff in, and the good news is that the
They left enough room in the container so that you can directly mix it right into the container. And then what you have to do is continue to stir it up, because this stuff has to be fairly well mixed. What you also want to try to do, though, is to not create a lot of bubbles in this stuff, because that means bubbles that you just have to get out. So you don't want to be too crazy about this mixing, and try to keep your actions as light as possible to avoid the bubbles. This is a totally different compound than we used originally, and this is basically the third different type we've tried. Reasonably pleased on this one that it's fairly soupy, so that it should allow us to get the bubbles and stuff out. We've also changed how we're constructing this thing, so this time around we're going to have a lot of pre-built cells, and instead of laying them in each individual cell, we're going to lay in blocks. And also we're going to put in a layer of this stuff prior to putting the cells down. Again, all to try to avoid air bubbles. Originally, we did a technique of just putting the cells in and then pouring over the top of them. You'll see a lot of videos online where they did exactly that, but it gets very difficult to get all the air bubbles out, because they get trapped underneath the cells.
Yeah, we wound up learning a lot from the very first solar panel we built, and we corrected the mistakes going forward. Well, the very first time you'd seen the jig that we showed you, the first one we didn't even do with the jig. We went ahead and laid it out cell by cell, and it was just taking far too long.
So this time we're going to try to spread it out and put a layer down.
And the main reason we're doing this is just, again, to have a surface to try to mitigate the amount of air bubbles. Probably a week per panel.
No, don't need to ask me about that. It's about 4 hours. So there's plenty of time on this stuff. That's what we look for as well, was one that had a very long setup time.
Yeah.
Yep.
Yeah.
What was the question?
She wanted to know if we use a light panel underneath so that we could see a lot of this better, and the answer was yes. It made it a lot easier to spread it, to know the surface we had gotten, where it was cooling at, and then you'll see later, I just have photos of it, but it helps us get out air bubbles because we can look underneath and see where the air bubbles are.
Is the active surface of the solar cell being put down?
Yes, the active surface goes down,
Okay.
right against the glass.
And we're going to be showing that next here.
Why are air bubbles such a problem?
The biggest problem with the air bubbles is that it creates an area that can possibly heat, where the solar can have a little bit like a greenhouse type action, and uniform heating across a solar cell could eventually lead to cracking.
Yeah, which is why commercially they're using the vacuum chamber. They're wanting to get all the air bubbles out of the whole process. Right. Okay. If you guys want to move in, I'm told that the hallway's pretty packed, so feel free to move in. There is some extra space.
We can put some people in here.
Yeah.
How much was that bet?
Yeah.
Well, sorry?
How much was the bet for 20 people?
Oh, he's buying me drinks tonight. And after a long day.
Spacers and markers down. Yeah. more than one container. We think we can do it with about 4 of those containers.
It wound up being about $100 total.
Yeah, we think we can get away with a little less, but we got crazy with it.
And it's kind of puddled, but that doesn't matter as long as it's not over.
Correct.
Yeah, you try to get rid of the puddling as much as possible, but you still have quite a bit. And you do have to be careful once it's pressed down.
A couple more of those little tile spacers, at least temporarily, here to hold positions. They can lead to failure. The air pockets themselves can lead to failure. And it could, the air pocket itself can create a little bit of a hot spot on the cell, and then because it's just a small portion of the one cell, it can differentially heat and then eventually possibly crack.
And with the encapsulation fluid also, you will want to, I think we're going to have one where we're weighting it down a little bit. But we did have some cases where it had pooled a little bit too much in one place and came onto the back of the solar cell. You just have to be careful, make sure to wipe that up, because you're going to want a clean contact for the back, because we're
Now,
two sections here.
For the time being and stuff, I'm probably going to go ahead and weigh these things down slightly. Got a mess of bolts and stuff that we've used for other stuff here.
Yeah, so we suspect as we get a little bit better at the process, maybe we'll use a little bit less of the encapsulation fluid.
Can't use a roller of any kind?
Yes, you can get away with a little bit of a roller. Once again, you have to be very careful because these things are so fragile. We have to use the squeegee initially, one of the same things you use for like silk screen printing, and just drag the stuff across. But these things are so fragile that you have, just one mistake. I mean, you hit an edge, and next thing you know, it's like, oh man.
Assume you can replace.
We're going ahead and applied.
Sorry?
I assume you can replace it.
Yes. Yeah. In this process, we did have a couple that broke en route, and we did go ahead and go back and replace them. So we've got about a 4-hour window where things are still kind of viscous. We can indeed go in and make a repair if we have to.
No. Yeah, I was going to say the painful part is when, during the process of trying to get all the bubbles out, you wind up cracking one of the cells without realizing it. You're already in the process of laying on doing the encapsulation. And actually on this one that we're showing, and I'm not sure I have a video of it, but we actually did have a crack in one of the cells.
You wouldn't want the video.
Yeah, I took that one off because there was lots of cursing involved when we...
We've gone ahead and applied flux to the points here on the backs of these things. And then it's just a matter of getting these things to flow and adhere. Sometimes it doesn't produce the most gorgeous joint on this thing, but the only thing you really need to worry about is making contact. So I try to go over both sides of the ribbon.
Yeah. You can replace it almost pretty much at any time up until once you start into the whole encapsulation. Like we had just finished everything. We poured everything on top and let it sit, and then we found out that a corner piece had cracked.
Now you can indeed survive some cracks. In other words, even though you may have a couple of nicks, if it's not on the complete cell, you can get away with it. It'll still operate. It'll still be
and operate well, oddly enough.
Yes. And what I'm doing is I'm preloading the tip with quite a bit of solder, and then coming and hitting it so it's almost like a solder tack. The only thing to tell you is that it at least does produce a good solder joint this way. Again, it may not look pretty. In some respects, but it's going to be very, very functional.
Okay. I had talked about the getting the air bubbles out, and this is essentially the process that we just use to find the air bubbles. So we just look underneath because we have the shop lights shining up. And this is kind of what we're talking about when we're saying air bubbles, where you're getting some air underneath the cells. So in the process of spreading it out and laying it down and even putting a little bit on it pressure to try to get that out, you still have a little bit. And all we wound up doing was just reaching our hand on top and kind of massaging the air bubbles out. And this is the end result of this particular solar panel. And I don't think you can see in this photo the one cracked cell, so we're off the hook for that one.
What does that weigh when it's done, one panel?
It's fairly lightweight, mostly because we used a fairly small aluminum. But I'm not sure, 40, 50 pounds, 50 pounds maybe, 45 pounds?
Yeah, probably.
Yeah. We do use two of us to handle it, though. I have indeed moved it by myself, but most of the time it's...
How thick was the glass that you used?
That's about an 1/8 inch thick glass, and tempered glass, so it's reasonably heavy. Yeah, of all the weight on there, the glass is the heaviest.
Yeah.
So will hail hit it and break it?
No, these things should be hail resistant up to a point. And again, that's the reason for, oh, there was a question about hail on these things.
We've had that question before.
Yeah, a commercial tempered glass that should be very hail resistant.
Yeah.
I think up to about a...
3 by 5.
Roughly.
Roughly, yeah. And don't feel that you necessarily have to go by the exact dimensions. It just, we worked with what we had. We figured out how to lay them out, how much we could get out of it. And because we found somebody who had these available for that price, we jumped on it and grabbed them. So it doesn't have to necessarily fall into that realm.
The biggest problem is going to be scratching long term.
Yep.
In other words, where wind, you'll get an abrasion on the plastic surface.
And that's where we had also talked about the scratch resistant. We had looked into that as well. But that's the main concern with that. And the only reason we avoided it entirely was just because of cost.
We thought seriously about having a sacrificial surface, or something that we knew, one surface that we had to replace every 3 to 4 years.
That sounds like a pain.
That's a lot of work for one.
Yes.
Yes.
Yeah.
Is that $5,370 your learning curve built into that?
Okay, these panels are worth about $5 million if you're taking a learning curve. My
Because
goodness.
I'm figuring, how much money am I going to save until I get to the point that you're talking about?
That's a valid point. The cost that I outline is what we've spent. So that includes breaking and smashing cells that we've. Thankfully, when he shipped them out, he shipped extra because again he got these at auction. They weren't exactly 6 kilowatts. He just piled them in a box and said you have some extra. So we had a little bit of wiggle room. But the main thing with the learning curve and having an expense to that. The biggest part was the breaking of the cells. It takes a while to get used to how fragile these things really are. We thought they were exaggerating when people were talking about how fragile they truly are. Very, very fragile. So that's and the cost to us, because it was 27 cents a lot. It really wasn't that that much of a concern for us in terms of the cost.
Do you have classes where people can come in and make one panel, and if not, will you, for me?
Are you going to fly to Kentucky? I was going to say, well, we don't have classes. This was, oddly enough, it was just a father-son project. We decided and some people go camping, we go to the shop. We're here as an exhibitor, Earthineer, so we're a social network for sustainable living. So topics like these are things that are covered, and what we endeavor to do is give step-by-steps and do everything open source and let everybody know this is what we're doing and this is how we're doing it. We don't have classes per se, so we don't make any money on classes. We don't run any in Kentucky. We've been putting up videos, and like I said, we're going to have a step-by-step, so that's probably the best you can hope for in terms of that. I mean, obviously, if you want to fly to Kentucky and you'd like to step through the process in the shop, we'd be happy to accommodate you. And if this had been the Seven Springs event in Pennsylvania, we likely would have brought some of the solar panels with, just so, you know, more of a tactile experience. And that was part of the reason why we recorded the videos in the first place, is we didn't want to just show pictures and explain. We wanted you to be able to see some of the process. Yep.
I didn't get the acrylic resin that you used. What was the name?
That's a good question. What was the name? Thank you. Solar-Tite.
Solar-Tite, the question was the resin,
Yeah.
Solar-Tite 384.
Is that all going to
Can
be
you take
on
questions at the end so that we can get through the material?
Yeah, okay. Yeah, we'll go ahead and, let me see, how long do we have? Okay, it's 1:38, so we still have some time. Some of the other things we were going to talk about were the testing, go on to storage and things like that. You?
Okay. How we wound up doing the testing. This was, some people had asked a question of how we were going to finally connect these things. And all we wound up doing was just using some stainless steel bolts, some crimp-on type connectors, and then once these things were in place and all hooked up, we were just going to go ahead and cover it with silicone to keep the weather out and everything else. The only other step that we did do, though, was we made, in addition to the crimp, we soldered as well as crimp. We found that out in our own products and business, that the additional step of soldering the crimp connections and stuff, long term, does a much better job on the joint. All we did was we took the panels and put them under load. We wound up using a grid tie inverter to simulate the load, and then we measured the voltage and the current to just double check how these things were operating. The current meter was a specialized thing, though. It's a DC clamp-on type, but the voltmeter is just a standard thing you can get at Radio Shack, Home Depot, whoever. Of all the parameters, though, the voltage will perhaps be the most important, because that will definitely tell you if you've got a problem. And most of the time, if you've got the voltage, you've got the current. We also worked on a way to support these things. We found out that out by us, that roughly about a 45-degree angle on these things from horizon gave us the best results season to season.
Yeah, we're going for a little bit of a two-thirds rule with that.
And here's everything monitored all at the same time.
Some of this we'd already covered earlier, but this was a breakdown of all the costs. So this was the costs, even through the cells that we broke and everything. This was the cost that we wound up doing. So we had the cells, 27 cents a watt. We had 6 kilowatts worth. The frames, again, we had 30 frames, so it's just a multiplier. The frames, the tempered glass. We talked about the potting and how much we spent per panel on that. And so that came with the price. There were some ancillary, costs, the solder and stuff like that we didn't really include in that, but
the extra beers. The beers.
Yeah, and those as well. He talked just briefly about the positioning, so I won't go a lot into that. But essentially, we were going for more of a two-thirds rule to try to get the optimal angle for to cover all the seasons. The other thing that we're looking into is having some variance on it from season to season as well, and just basing the angle off of that. So that may be a future endeavor.
Making them movable and just adjusting them 4 times a year to try to get the optimum. Wanted to go into this just a little bit, just so that people would understand some of the differences. AC is alternating current, DC is direct current, and DC stuff you just turn on and the power is there. With the alternating current, it's going through a cycle of high and low through a sine wave type cycle. Normal DC types are batteries, solar cells, most wind turbines. The AC types are more of generators, and it's mechanically manufactured for the electricity. And the way that we get, though, from the DC to the AC is to wind up using inverters so that we can bring it into the house and use it just like you would, plugging into the wall. One thing that we've discovered, and we're getting more into this, is why not just stay within the DC realm? What's interesting from a historical standpoint is that when electricity was first being used in houses and stuff, it was DC. And it wasn't until they started doing AC generation and allowing the power to go more distances that AC became prevalent. But nowadays, there's a lot of stuff that we can do in the DC mode. And one of them that we've been playing around with that we've really been impressed with are very small DC to DC converters. And considering doing some of your conversion of DC and even conversion, again, of DC into AC in little micro electronic units and distributing it. So this is one of the DC to DC converters that we've been playing with. The way that they work is they bring the DC in, they chop it at a very high frequency. Because of the high frequency, all the components are very, very small. There's a transformer, then once again you rectify it, and then you get a stable, very stable DC output. And the solar panels, in case you don't realize, go up and down in voltage with the amount of sunlight that's hitting them. So throughout the day and stuff, you'll see a varying amount of DC voltage coming out, but with a regulator of some kind, and a DC to DC type, which is very efficient, you can definitely control and lock that voltage. Next, if you do want to stay in the AC mode, you have to worry about inverters. And the standard inverter is you go ahead and you have your solar panels operating into an inverter, usually maybe some sort of a transfer switch, and then finally into your house wiring and appliance. There is a new type of device called a grid tie inverter, which allows you to take some of the things out of the steps and stuff, where you just take your solar panels, a grid tie inverter, and directly into the house wiring. And it takes and it syncs itself up to the grid and just supplements the power and stuff that's on the grid. And if you make enough power, you can supposedly sell it back to the power company. This was one of the grid tie inverters that we were playing with. We have played with both the standard inverter and the grid tie inverter. And the grid tie inverter, though, does have one bad problem. And that nowadays, they're required to conform to the National Electric Code. And if the power from the grid goes out, the grid tie inverter goes out as well, and for protection for the folks that would be working in the power lines. I'm hoping that someday they have a unit where you can switch that function off. But for safety issues and stuff, I don't think that they're going to be doing it anytime soon. So what you wind up maybe having, if you want the best of both worlds, is both a grid tie inverter and a standard converter. Next, most of the time when you're dealing with the solar panels, you're going to want to store it. Store the energy somehow so you can use it again later on. There are a whole bunch of different ways to do this, and here's the list. The pure chemical one I may make a little bit of a mention to. A lot of people have been taking power from the solar panels, using to do electrolysis and getting the hydrogen and oxygen back out of water, and then using fuel cells then to recombine and get the power back. The most cost-efficient one, and the one that everybody seems to use a lot of, is electromechanical, and specifically the lead-acid type batteries. Those are going to be the cheapest and easiest to use. In our particular stuff, we've been using the deep cycle lead gel type batteries. They're quite good, they're reasonably inexpensive, and they work.
And we had them on hand because we had them for the electric car.
Mm-hmm. So we had a bank of these things available. And then finally, you know, there are some interesting things coming around in terms of exotics, lithium, sodium, and some nanotech. So it's going to be interesting to see where this all winds up going in terms of storage. The last one that we've been playing with a lot ourselves has been the ultracapacitors, which gets into the pure electrical range. And these things allow you to do a very fast charge and discharge of energy. So beyond that, I think that we've been very encouraged about what we think is going to be the future for some solar stuff, and specifically for doing a lot of storage and stuff off-grid. We do think that a decentralization of power, that there's going to be a lot of benefits to it.
Okay. We'll go ahead and answer questions now. And I will say ahead of time, yes, we will be putting all of this online, and we're actually going to be making a more thorough step by step as well. So everything should be pretty well detailed. Thank you, everybody, and feel free to stop by the booth if you have more questions.